Hi there, this video is about mass spectroscopy. It is a new topic for AP Chem, but I'm hoping we can tackle it. It's not too far from isotopes actually, and in fact you've already looked at some questions with mass specs before and you haven't even known it yet. I think you've done pretty well. Let's give it a tackle here. I want to relate this to something that you might have done before. Let's say you are living at this house and it's a hill, the driveway has a slant and it goes from the top down to the bottom. And at the very top by your garage door, you're putting a bowling ball and a tennis ball, and you put them at the very top, like right next to your garage, and you're going to send them down the hill. So down your driveway they go, and on the grass part, you're going to shoot a garden hose at it. Now, if you shoot a garden hose on full stream at a tennis ball, is the tennis ball going to move? I would say yes. I would say that tennis ball is going to move and end up slightly on the side here of your house. The tennis ball will end up probably over here. But if you're going to shoot that same garden hose at a bowling ball, I'm going to bet that bowling ball is going to keep rolling right down. It is much heavier and it is not going to move from your garden hose. Mass spectroscopy works the same sort of way. But instead of using a garden hose, we've got to do something different. The purpose of mass spectroscopy is to tell us what isotopes are inside of atoms. If we can't physically hold atoms in our hands and find what their mass is, how can we ever know which one has more neutrons than the other? And besides, a neutron is so small. One neutron change, we can know the difference? We can, and it's as simple as using bowling balls as tennis balls. Atoms are just a little bit different. So let's take a look. Okay, so you got an atom, and you need to be able to separate them into their different isotopes. How will you do that? Number one, you can't use a garden hose with an atom. That just doesn't work. So what could we use instead of a garden hose? I'd like to propose, what if we use something like a magnet and we charge that atom? Suddenly the atom has a charge and it will go toward the magnet or away from the magnet, depending on which way you've orientated it. So in that way, just like a garden hose can push a bowling ball or a tennis ball, I'm going to have the magnet push an atom, a charged atom. Let me flip my screen here. So I want to take you through what a mass spectroscoper kind of looks like. This is what like a real one would kind of look like. You can see we've got a magnet here. And what we're going to do is send the sample inside. Now the sample is going to be like all one type of gas, like all neon. And I want to look at what are the different isotopes that come out of neon. And it's going to shoot through this tube and be detected on the other side. This picture over here is more cartoony, but it actually kind of makes more sense. So a real spectrometer kind of looks more like this, but the same idea happens in this cartoon one. So you can annotate that one there. I'd like to take you through this one though. Let me get to my screen. Okay. No, come on. All right, I got my video going now. So I have this machine going on, and you can see those little dots kind of shooting out. We'll talk about that. The first thing that happens is I'm going to shoot the sample inside. That's the green parts. So that's like the neon I'm shooting inside, for an example, if I want to find the isotopes in neon. So I'm shooting the sample inside, and then you can see those the tan squares. The first thing I need to do is heat the sample so it's a gas. Now, naturally, neon is a gas, so that's not the best example. But let's say it was something like copper. Copper is not naturally a gas, so we're going to vaporize it, make it a gas, and then send it through, and then we're going to shoot electrons at it. The electrons will force the electrons of the copper atoms to shoot off, or the neon atoms to shoot off. So suddenly you've created an atom with one less electron. One less electron means it's a charged particle. So now this positively charged is going to be pushed and pulled by a magnet, and that's what these blue circles are. And the charged particle is going to shoot through the blue circles. It'll accelerate through the blue circles, and the magnet is the dark gray part. You can see that looks like a backwards C. And there the magnet will push and pull the atom according to how heavy it is. Take a look at the colors as they come through. You can see the chart in the top right there. If you watch that pink guy, he goes really close to the side, but the yellow guy, he's really far on the right side. Watch another pink guy. He goes on the far left side. It makes a big curve. The yellow guy, not so good at curving. The yellow guy would be like the fat guy, the one that has more isotopes. The fat guy, the fat atom, can't take the corner so well because he's just so big, it's just hard to take the corner. But the little pink guy, he can definitely take that corner because he's small and skinny, he has fewer neutrons. So right there we're able to see that all those different colors are the different massed atoms, charged particles in this case, and it shows the different number of neutrons they have. Okay, let's go back to my screen here. So there we can see that this one here would be the bigger one. It can't take this corner quite as well. That's kind of like the bowling ball. It can't take the corner very well. This right here would be like the tennis ball. It's smaller and it has fewer neutrons. It can take the corner pretty well. And in that way, we can separate each of the charged parts or each of the atoms by their size, by 1 neutron. We can do it that sensitive. Okay, so let's take a look here. What was the most important part? Well, when we're shooting it through, we're going to use a magnet to push and pull it, and it depends on how heavy or light it is. And that'll come out on the screen, the detector over here. The skinny guys can take the corner, the bigger guys cannot. That tells us how many neutrons they have. We could also have them take the corner differently, being pushed and pulled by the magnet using charges. Good news by AP is AP is never going to change the charge to +2. They're always going to have it be a +1 charge. So it makes it a lot simpler. So really the only thing that's going to be able to push or pull it is not by charge, because they're all +1, but by the size of it. And that tells us how many neutrons they have. And it comes out to look like a picture detection like this, which is actually like the isotope problems you kind of did in the Google form just now. Okay, so let's take a look. There are 2 types of spectrums. I'm going to take a look at this one, which is less common, but it just gets a little trickier. So let's take a look. This shows relative abundance on the left side, and then down here, this M stands for mass, and the Z stands for charge. Now you can, like I said, change it charge +1, +2, but AP never ever does that, and they would have to specify it in the chart. So really we can assume the charge is always +1, which means if you're dividing by a +1, it's really just telling you the mass. So this right here says the AMU, the atomic mass for these isotopes, is 10, and this one right here is 11. So it's saying that 100 of them came out with a mass of 11, and a mass of 10 had 23. It is not saying the percentage, like we were dealing with isotopes. It's not saying 100% of them are this and 23% are this. It doesn't work like that. So we got to be careful with that part. So 100 of them came out and 23 came out. They're looking at numbers. Now I need to change this into percentage. So my total here is going to be 100 plus 23, which is 123. Which means when you have a mass of 11, your percentage of having a mass of 11 out of this mass spectrum is going to be 100 out of 123. And that math for me is 81.3%. If you're going to have this mass of 10, then that percentage will be 23 of the atoms out of 123 atoms, which gives you a percentage of 18.7. So then if you had to actually calculate, well, what is the average atomic mass of this? Then I'm going to be taking, just like we did with isotopes, I'm going to take each isotope with its percentage and find its average sort of mass, its weighted average, in fact. So the first one, I'm going to say my mass is a mass 10. Oops, I can just put that in here. This is isotope 1. And it has a percentage of 18.7, so I'm going to say 0.187. This one over here is my mass 11. That's its mass of that isotope times its percentage, 81.3, so 0.813. And then all I got to do is add up those parts. This is isotope 2. So when I do that, I get a whopping 10.81. AMU would be the units here. AMU. Don't forget the units. AP will get you on units. AP will give you 1 point for the units on several problems. They'll have to specify that they're going to call for that, but you don't want to miss the units. So what is the average mass of boron, if that was the question for this problem? Be 10.81. And if you actually look at your periodic table, it would be 10.81. So that would be one way to show mass spectrums. I want to go backwards now. So we just found the percentage, and now I want to go back and actually create the mass spectrum from it. So the first thing we're going to do is calculate the average mass for sulfur. If you know what you're doing for this, pause it, do it yourself, and then come back and check the answer. I'll just kind of show you my work. Make it a little skinnier here. Okay, so the average, I'm going to do the weighted average of all of them. The only thing that makes this problem trickier is we've got to put it all in decimal place, and most people mess up this one. It's got to be 0.0002. That's taking the percentage and putting it in the decimal form. This one would be 0.0429, 0.0076. It's tricky like that, right? Because it's a very small percentage. 94, this is 0.9493. And that's how I'm going to use them. I'm going to set them up just like I did with this boron one. All right. So I'm going to do it of each isotope. Isotope 1, isotope 2, isotope 3, and isotope 4, and I'm going to add those up. 1, 2, 3, 4. So isotope 1, here's my mass, 3197, oh man, 972,071, and it has a percentage of the 0.9493. And I'm going to add that up with my second mass, 32.971458, and it has a percentage of 0.0076. The next guy, 33, goes in here, 33.967867. This is a lot of sig figs. 0.0429 would be its percentage in decimal form. And then my last one is my 35, 35.967081, and its percentage, 0.0002. I'm sorry if that looks a little sloppy. It's difficult to write on a screen. In the end, I'm going to multiply those, add them all up, and you'll get a lovely number, hopefully something around 32.07 units, AMU. Atomic mass units is what that stands for. All right, now let's kind of go backwards, because we found the percentages for each of them, and we were able to find the average atomic mass. What if we had to make the spectrum? We're just going to do a totally rough sketch. On the bottom, as you remember, it's mass over charge. Now the charge is always going to be a +1, make life easier. So the masses that I'm looking at are all these 31, 32, 33, 35. So I'm going to say 31, 32, 33, 34, 35. And over here is percent abundance. Now what we had before was the relative abundance. That's what this one was. But we're looking at percentages for this one. So I'm doing percent abundance on the side. I'll use a different color. And I just wanted to show the different sizes. Now most of them are that 31.9, just before the 32. And there's a lot of them. 94%. And then my next one is 0.076, just before 33. That's just a little bit. 33.9 had a 0.04. Oh my gosh. And this one's 0.02. Yikes. The point of this is that you remember what's on Y and X, and to put in the little lines, just give yourself a percentage, 94%, and then these are like microscopic kind of. Pause it here. Okay. All right, the last thing that we're going to do is tackle something that might look on the multiple choice parts. So for multiple choice questions on the AP test, you get 1.8 minutes on average per question. Now this one will be faster than 1.8 minutes. But if you think about it, if you had to do all this math, that would take you longer than 1.8 minutes. The other part about AP questions is you do not get a calculator on the multiple choice. So you have all these numbers, but you cannot do any of that math. If you did, if you tried, it'd be just too hard. So what we need to do is be able to look at it quickly. So I haven't gotten a periodic table to you yet. That's in my little lab packet we're going to get to you. But hopefully you got a periodic table of some kind, or you can look it up online. But what you want to see here is you want to do a quick glance. Like, what element is this for? First thing I want to take a look at, is this percent abundance? Yes, it is. Percent abundance. This has been 0.92. So 92% is this. And I want to look for an element that's going to have a mass of about 28. Sure, it's got a few here, but pretty much strong majority it's 28. So I'm going to go to my periodic table, take a look. Who has a mass around 28? Hopefully you'll see silicon. Silicon is Si. Let me get up my periodic table, but it's in my head. Silicon is Si. And you will find that its is 28.1. And